If not, thank you very much. And over to Dmitry Pekorovsky from San Diego. Do you all see his slides? If so, then Dmitry, yes. Please start.
Hello. Let's go to our next slide. Here's the overview of this talk. So this talk, I will talk about the P3DFFT, which is the library.
Dmitry, can you speak up a little bit?
Closer to the...
Is this better?
Yes.
Much better.
Thank you.
Okay. So P3DFFT is a numerical library that I've been working on. So first I will give a little background about fast Fourier transforms and then describe a P3DFFT. This library has been around for a while. So first I will just introduce the basics of it, and later I'll mention briefly mention the latest work I've been doing on P3DFFT as part of ECSS project. So let's go to the next slide. So fast Fourier transforms, of course, is one of the most heavily used algorithms in many areas of computational science. And it's been around for quite a while. There are it's a very computational demanding algorithm because it's not a cache-friendly algorithm, and in parallel implementations, it's very bandwidth intensive and communication intensive. Of course, there has been a lot of implementations of fast Fourier transform. There are many excellent packages out there, numerical libraries for it. The goal here is to provide a scalable implementation of three-dimensional fast Fourier transforms and other algorithms that kind of fall in the same class. Let's go to the next slide. I need to introduce just a little bit of technical things so that it can be easy to understand the following. Three-dimensional fast Fourier transforms. The algorithm is what you do is you apply one-dimensional fast Fourier transform. I won't go into what that is, but so you apply it 3 times for each of the dimensions, x, y, and z. And if you have a parallel program, you need to somehow make sure that each of the one-dimensional FFTs is performed on local data for each processor. So you need to transpose the data, send the data around, so that rearrange it so that when the time for FFT in a given dimension comes, all the data is local. This is the most efficient way to proceed. And then at each stage, there are just as so many one-dimensional FFTs to do, and you can do this work in parallel. Let's go to the next slide. So there are several ways you can decompose. If you have a 3-dimensional grid, that's your data. You can first of all, the easiest decomposition would be one-dimensional decomposition to cut it in terms of planes or slabs, and each slab lives on a different processor. Another way is to do a 2-dimensional decomposition where you divide the volume into pencils or columns, and then each column lives on a different processor. I'm just defining the terms here, so let's go to the next slide. So if you have a one-dimensional decomposition, the scalability is limited by n, which is the linear grid size, because you have so many planes. And that's not enough parallelism for modern systems that often have tens or even hundreds of thousands cores. However, most existing libraries today still use one-dimensional decomposition. That's why two-dimensional decomposition is something else is needed, and two-dimensional decomposition is what solves the problem, where concurrency is increased up to n squared. Next slide. So here is a brief overview of the three-dimensional fast Fourier transform algorithm with two-dimensional decomposition. We start out on the left with volume decomposed as pencils. Each processor is shown by its own color, so it's a 4x4, a total of 16 processors or cores, whatever. And we start by performing one-dimensional FFT in X dimension, followed by a transpose in XY plane to exchange among the rows of this processor grid to rearrange the data. So now we have pencils in the middle of the picture. We have pencils oriented in Y dimension. So all the data in Y dimension is local, and then we can do the one-dimensional FFT in Y. After that, we exchange again in YZ plane, rearrange the data so that we have pencils arranged along Z dimension, and we can do the 1D FFT in Z after that. Next slide. So P3DFFT is an open source library for efficient and scalable 3D FFT. It uses two-dimensional decomposition. Here's a website. It's available for download. It's actually started out as an advanced user support project. Then we generalized the software and made it available. Currently, it's supported by NSF SI2 grant, but in the past it was supported by Tegrate and other NSF grants. Let's move forward. Next slide. Okay. So here I listed the main features of P3DFFT as it is today. It implements real to complex and complex to real three-dimensional Fourier transforms. It also implements cosine, sine, Chebyshev transforms in a third dimension as an option. For many scientific codes need this option. It has both Fortran and C interfaces. It can use single or double precision. It can handle arbitrary dimensions. It doesn't need to be evenly divided. It can do either in-place or out-place transform. It can also do pruned transforms. I'll explain later what these are, and also multivariable transforms. Next slide. Here I'll show some scalability results. These were obtained on Myra, which is an IBM Blue Gene Q at Argonne National Lab. So you can see that scaling is pretty good, all the way up to 500,000 cores. We have a variety of grid sizes here. So yeah, next slide. P3DFFT has first it grew out of a project, of advanced user support project for turbulence code. So turbulence is the area that I will talk a little bit about later. That probably has the most use of this algorithm, but also there are many other fields that or already use P3DFFT or potentially can use P3DFFT because they use this class of algorithms. So we have turbulence, astrophysics, oceanography, and material science, chemistry, aerospace engineering, X-ray crystallography, medicine, atmospheric science, and possibly more. It's a very ubiquitous algorithm. Next slide. So here, mention briefly the turbulence. Turbulence is characterized by disorderly nonlinear fluctuations, 3D space and time, that span a wide range of interacting scales. So DNS stands for Direct Numerical Simulations Turbulence, and it's important too because it does a first principles simulations of turbulence. No approximations made. However, it is extremely compute-intensive algorithm because of this. What I said about disorderly fluctuations. It's important to capture a wide range of scales. So it's important to use typically very large grids are used, and the high end of HPC systems are used for these kind of simulations. And it's very important to understand the fundamental properties of turbulence. Next slide. So typical DNS simulations use a so-called pseudospectral method to solve Navier-Stokes equations, and 3DFFT is the most time-consuming part of that algorithm. As I mentioned already, two-dimensional decomposition is necessary to take advantage of large core counts available on modern HPC platforms. So P3DFFT has found a lot of use in various DNS applications. And let's take a look at the results from one of them. Next slide. This is performance. This plot shows scaling performance of a DNS code. In this case, shown on Cray XT5. Up to 128,000 cores. Next slide. So now I will talk about the ECSS project with P3DFFT. This is an internal project, and its goal is to create a community software for P3DFFT. So first of all, we created a new and improved version of P3DFFT, version 2.7. That includes improved C Fortran interface that's necessary for C codes calling P3DFFT. It also introduces multivariable transforms, where several independent variables can be transformed in one call. So, for example, if you have a vector, let's say a velocity vector with 3 components, and the algorithm requires you to transform all 3 vector components, you can do it in a single call. And in certain conditions, if there is a low grid size or high core counts, that can actually save time due to message aggregation. So it can be more efficient than just transforming one component at a time. Another feature added here is pruned transforms. It can be on input or output. So, for example, consider the so-called two-third rule for de-aliasing in DNS turbulence simulations. What it requires is that on forward transform, 1/3 of the highest frequencies are thrown away after the transform. They are not needed for the algorithm. And before before doing the inverse transforms, the array is filled with zeros in place of these highest frequencies. So if you just apply a 3DFFT, standard 3DFFT, it will work. However, there will be a lot of extra work and extra data communicated. So it's possible to save some time if you know that these frequencies will not be needed. So that's what a pruned transform does. It just makes sure that you're not using these a certain specified number of frequencies. This allows one to save significant time. Next slide. So under this project, P3DFFT has been ported and extensively tested on XT systems, including Stampede, Gordon, Trestles, Blacklight. And it has been installed as community software now on Gordon and Stampede. So we created module P3DFFT for the most common use cases. In case custom installations is required, it can be easily done by following instructions. The software is documented, first of all, on there's an Exceed page here on portalexceed.org, and P3DFFT now has a GitHub page where you can download P3DFFT as well as see all of the documentation there. Next slide. So here's how one would use P3DFFT. It's pretty straightforward. You first need to load the needed modules, and the modules you need is FFTW and MPI, and then you load module P3DFFT. And write your code, just making sure to include the necessary files, P3DFFT.h in C, for example, and then call P3DFFT setup to kind of get started. Fortran and C has a slightly different syntax, but it's all in the user guide. It's pretty straightforward. And then just call P3DFFT ftran, for example. That's a forward transform function, or there's also backward transform. After you write your code, compile it with the include file and link code with the library. Next slide. There are sample test programs that are included in the installation, both in Fortran and C. So those can be used as an example of how to write the code that uses P3DFFT. Also, they can be used for correctness testing and for benchmarking. So there are examples for most cases that I can think of using it. There's test sign, test Chevy, test random, and so forth. Next slide. So let me talk a little about the ongoing work. As I said, this work is supported by an NSF SI2 grant. Basically, we want to generalize the structure, the framework that we have right now, P3DFFT, to include even more usage scenarios. So we want to expand the capabilities beyond what we have in several ways. One way is to include more transform types. So it will be not just real to complex, complex to real, FFT, but other types of spectral transforms, as well as more generally, we will include compact schemes. I will talk briefly about that later. This work will include arbitrary memory and processor layouts to have flexibility in how a user's applications can call P3DFFT. It will have isolated transforms in 1D, 2D, in addition to 3D. We will add ghost cell support. And, I already said about compact schemes as an alternative to spectral differentiation. Next slide. Yeah, this is basically showing the diagram for the future package. Next slide. This is an example of work in compressible turbulence. Compressible turbulence flows are critical in many natural engineering systems. And this plot shows scaling of CDNS, which is a DNS code for compressible turbulence that solves compressible Navier-Stokes equations using tensor-order compact schemes, using a very similar algorithm for P3DFFT. So that's why we are attempting to generalize P3DFFT to go beyond just the Fourier transform. Next slide. And the second part of this work is maintaining and improving performance. Currently, we are using P3DFFT uses MPI all-to-all as the main communication routine, which is a blocking collective call. There are ways to improve that, and we always need to find ways to improve because it's a very communication-intensive algorithm. So there are several ways we are exploring right now to make it even better, based on one-sided communication using either MPI2 features or MPI3 features, OpenSHMEM, and Core Fortran. And we are attempting to use communication computation overlap, as well as hybrid MPI OpenMP. Next slide. Here I mentioned coarse-grain overlap, which is the idea that if there are several independent variables, such as velocity components, we can overlap communication stage of one variable with computation stage of another variable. Next slide. These are some results of work with coarse-grain overlap. These results were obtained on Mellanox ConnectX-2 cluster. We see anywhere from 10 to 20% improvement in total performance based on overlap. So that's an encouraging result. Next slide. So in summary, P3DFFT is now an official XT community software. It's been installed, tested, and documented. It is already popular with domain scientists in several fields, but work is ongoing to expand its capabilities and adapt to even wider range of possible uses. If you have an interest in collaborating with us or even testing this software and providing feedback, please write to me. I'll be happy to hear from you. Thank you.
Thank you very much, Dmitry. Excellent talk, I thought. Questions for Dmitry?
Yes, this is Mona. I have a question. Now, I'm not a data scientist, so excuse my ignorance, but I was wondering, I have a project that is looking for tools, and their data is time series signal analysis data, and I was wondering if your tool might be useful for that purpose.
It might be. This is I should say this tool is for three-dimensional Fourier transforms. I don't know. Probably if you have time sequence, most likely that's a one-dimensional Fourier transform, and there are many well-known libraries available for that. So I'm not sure this is the best solution, but I guess I need to know more.
Okay, and since we're at the same place, I'll talk to you offline, and maybe we can clarify a bit. Thank you very much.
You're welcome.
Other questions?
This is Don at NCAR. Where did you say that the very nice presentations today were published?
Well, you're asking about the presentations?
Yeah, the PowerPoints.
Oh, the PowerPoints. So first of all, there will be a recording on the ECSS Symposium website, which I guess started right about on the second or third slide of Junqi's. But I think we can also I know we can also upload the presentations right there. Plus, I have them, so I mean, you know, I can send them to you right now, and the authors can too. So
that would be great.
The slides are on the website. I'm sorry, this is Natalie. The slides are there.
Oh, okay, great. Any questions right now? I guess Dmitry certainly communicated his email address, and I think you can find Junqi's also, and they're on the slides, I guess. But if you can't think of it now, then you can always find the authors later. So with this, I guess, if there's no further questions, thank you very much for attending today's call. And we will see you next month at the next ECSS.